And good afternoon, everyone. Thanks for jumping on for another ATS University. My name is Zach Allison with ATS. I'm our National Accounts Manager, working with engineer and architectural firms all across Canada and the US to help them get set up on the system. ATS SpecTool, in case you haven't heard of it before, thanks for jumping on to one of our sessions. Hopefully you find it beneficial. We do a number of these ATS University sessions to explain whether it's a application specific demo where we're talking about different products and how they fit into an application, or product specific demo like this, where we're going over the design details of how you select the right product, what are the various options that are important, or we do some code specific ATS University sessions as well. All of those sessions are recorded and are available on our ATS University page on the SpecTool. I'll show you at the end how you can find the previously recorded sessions if you want to come back to this pump sizing explanation and understand, reference back to any of the points that we covered today. For those of you that may or may not know, ATS is essentially a number of different manufacturers that have come together and sponsored our service, which allows you to properly configure, select, and then download the product selection in about 10 different output formats to make it easy and fast, to put to go from product selection and sizing to product on your drawings or specs or schedules, whatever it is you're using. We'll dive into that a little bit more detail later on, but with me today is Chase Wertsmith, EIT over at Zoller. He's been traveling across the US doing presentations and helping engineers understand, not just what the important product attributes are of the Zoller pumps, but more importantly, how to size and select and configure these pumps properly. There's a ton of different options that come into the pump game. It's not just as simple as, oh, I need a sump pump. So what are the important questions that you need to be asking yourself when you're making a selection? What are the design details that you need to uncover? And then how do you choose the right pump is what we're going to cover today. So one of the important pieces of housekeeping before we pass it over, everything's recorded. With that in mind, we do have everyone muted upon entry. Please feel free to put your questions into the Q&A chat. I'll be monitoring that as we go, and I'll raise that up to Chase as we get to a good point to pause. And of course, if you are looking to report this for your CPD hours or any of your professional development, I'll be sending out a certificate of attendance just in case you need that, so you can self-report this for your hours. I guess with all that being said, I'll pass it over to you, Chase. Let's dive in.
All right. Yeah. Thank you, Zach. So Zach's already introduced me, but again, my name is Chase Wertsmith. I am an application engineer at Zoller Pump Company. So I assist with pump sizing and basin sizing, as well as the sizing and selection of equipment for systems like low pressure sewer systems and on-site treatment systems and various other larger systems that you may find in the pump world. So today we're going to be going over pump sizing basics and system head curves. So with that, let's jump right on in. So first off, why use a pump? So mainly, we're no longer constrained by gravity. Pumps allow us to move water from a low elevation to a high elevation. They allow us to move water from a location that we don't want it at to a location that we do. So they do this by overcoming elevations, but that's not the only benefit of using a pump. One thing is capital costs. So pump systems are typically less expensive in the long run than, say, a gravity sewer system because of the smaller pipe diameter that you can use with pump systems, as well as the lower excavation costs. Since you don't have to dig nearly as deep, you don't have to maintain a certain slope to keep solids moving throughout your system. That pump is doing that for you. Pumps also allow for flow equalization, which basically means we have control over the flow throughout the system from beginning to end. So we know exactly the amount of water that is going to be moved whenever that pump turns on. And you can also use pumps for various alternative treatment systems like low pressure sewer systems and drip systems, both requiring certain pressures to keep sewage moving throughout that system, as well as various other systems you may find out there. So now that we've covered why to use a pump, now we should cover which pump do I use. So with that, we're going to address the various pump styles that are offered, as well as the questions that you need to ask when you are sizing a pump. We'll cover what a pump performance curve is, as well as why sizing matters, so why we're doing this presentation in the first place. We'll also cover the fundamentals of pump sizing by going through a short example, and then we will also go over system head curves and how to utilize them for the best possible design. So first, we need to know our pump styles. The first pump we're going to go over real quick is sump pumps. These have very minimal solids handling capability up to about 1/2 inch. The main reason why you need that is for any kind of solids that you may find in the groundwater. And these pumps come in automatic or non-automatic. And what I mean by that is an automatic pump typically has a float switch on the side, like what's pictured on the screen here. And all you have to do is drop that pump in, plug it in, and that pump is ready to go. You don't need any kind of external start components. When you're using a non-automatic pump, you don't have that float switch. So instead, you need an external start component like a piggyback float switch, or you're going to need a control panel with multiple float switches to turn that pump on and off. The main advantage of a non-automatic pump is you have much more control over when that pump turns on and off. You have control over how much the basin or wherever that pump is located at, how much that pit fills up with water before it turns on and drains that liquid. Then we have sewage pumps. Sewage pumps handle 2-inch solids or larger. That's typically a requirement by various government agencies to make sure that the solids that you may find in your wastewater is not getting clogged in your system. And these are also automatic or non-automatic. Then you have grinder pumps, which is sort of a specialty sewage pump. Grinder pumps reduce solids to a slurry. Now, the main benefit of that is A, you're not going to get nearly as many clogs as you may see in a sewage pump. And B, it's much easier to move water that has very small solids in it versus moving water with 2-inch plus size solids. So these pumps can put out a whole lot more pressure, which is why you typically see them being used in systems like low pressure sewer systems. And these come in automatic or non-automatic. And then lastly, we have effluent pumps. Effluent pumps are very similar to sump pumps, as in they have the same solids handling capability up to about 1/2 inch. However, they're non-automatic only. The main reason for that is that in effluent applications, such as septic tanks, you have hydrochloric gases that will eat away at your pump. They'll eat away at your the cast iron. They'll eat away at the seals. So you want to keep that pump submerged at all times. The only way to keep a pump submerged at all times is to have the float switches above the pump. So because of that, that pump will stay submerged in that water at all times. So now we need to cover what you need to ask when you are sizing a pump. And this is arguably the most important part of this presentation, because if you don't have all the questions answered, you're not going to be able to select a pump properly. So first off, you need to know what are the electrical conditions. So what is your voltage? What is your phase? So 208 volt power is not the same as 230 volt power. 3-phase pumps won't run on single-phase power, so it's always important to understand your site conditions. You also need to know the cord lengths that are required. So basically, you need to know where your pump is going to plug into. You need to know the location of the control panel. One thing about junction boxes. You need to know if you're using a junction box or not. That will also determine your cord length. However, I always recommend to not use a junction box, to instead have a direct connection to your control panel, mainly because you're just introducing another failure point into your system when you use a junction box. However, if you do need to use a junction box, I recommend not putting it into the wet well, to instead keep it outside of the wet well, because it's very easy for condensation to get into that junction box and fail the pump, or for water to trickle through those cords to the control panel itself. So that's just some advice I like to give. Another thing that you need to ask is whether or not it's a residential, commercial, or municipal level job. You're not going to be using a municipal level pump like the one on the right in a residential type application. So you want to make sure that you know what kind of application you're putting these pumps into, because some may be over-engineered for smaller systems. Next up, you need to know, what are you pumping? So are you pumping sewage? So anything that's going to go down a sink drain, or anything that is going to be going down a shower, or if there's going to be fats, oils, and greases that are going through it, that'll typically be a sewage pump or a grinder pump. You need to know if you're pumping effluent. So real quick on typical effluent applications, you'll typically have your wastewater coming into the inlet of the septic tank. And inside there, that water will typically stay in there for around 3 to 4 days. And during that time, uh, the solids are going to separate from your water and form what we call the sludge layer at the bottom. Whereas the fats, oils, and greases is typically going to float to the top of the septic tank into what we call a scum layer. And in between the two, you will find what we call effluent, which is still dirty water, still sewage water, but it's cleaner than what it was when it came in. And this is primarily what that effluent pump is going to be pumping out. So all that sludge and scum is going to stay in that septic tank, where all you have to do is treat the effluent water, which is typically going to have very small bits of sewage in it, as opposed to 2-inch, 3-inch, or larger solids. And then lastly, groundwater applications is going to use sump pumps. So typically in a basement or a golf course field or something like that.
So a couple questions coming in just there on I guess like the types of pumps to what products. We had a couple of questions coming in. Just seemed like a good time to bring it up. Maybe you can rhyme them off and you can tell me if it fits into the sewage, sump, grinder, or effluent. So the first question was on grease wastewater. Where does that fall in? And I think that's probably more of a specialty application, correct?
What kind of wastewater?
What type of pump can be used for grease waste?
Grease waste. Typically you're going to be using either a grinder pump or a sewage pump. I mean, I would say it's a specialty application if the only thing that's going to be in there is grease. In most sewage applications, you're going to find some grease, um, specifically in like residential applications and stuff like that. But if you're primarily pumping grease, I think that's going to be a completely different pump, if that's the only thing that's going to be going through them.
I imagine as well that's probably after a grease interceptor, so it should be relatively clean in comparison.
Yeah.
So that's certainly one. Another one pretty common that comes up, weeping tiles. Would that just go into your sump pump, you think, or is that into a different?
That's a good question, and unfortunately one that I don't really know the answer to, because I've never dealt with that before. But
one of the things
yeah,
that you might need to consider there is, in your weeping tile application, how much solids are you probably expecting? That's probably going to determine the level of pump that you need. If you need a solids handling pump that's handling larger debris, you've got stone or anything that you're expecting. But in general, that's probably your decision point there. And then the last one, which I think you covered, sinks and basins, especially in residential or say office commercial kitchen applications, like a cafe sink.
Are you asking what pump would be used for something like that?
Yeah, something like that. So like an
Yeah.
office cafe.
Yeah, typically you'd have that should all be going into wherever if you do have like a sewage pit or a pit like that, then that's where it'd be going. Is you'd either be using a sewage pump or a grinder pump for that. Um, Typically, I would say try to avoid putting any kind of grease down a sink. No pump really likes having grease go through them. No system really likes it either. Float switches can get clogged with them as well. So, uh, but yeah, I'd say you'd use either a sewage pump or a grinder pump for that application for sinks like that. Any kind of sewage, any kind of drains like that.
Thank you.
Yeah. Did that answer everybody's question so far? Are we good?
Yeah, I think we're good.
Fantastic. All right, let me skip right ahead to where we were at. Okay. So, continuing on what to ask, you need to know what your design flow is that will typically be in gallons per minute or liters per second. You need to know what your static head is. So this is going to be how high are you pumping? So are you pumping 10 feet or are you pumping up 50 feet? That's going to determine that's going to put a lot of pressure on your pump. You're typically going to account from the high point or from your outfall of the system down to the lowest point that your water gets to in your basin. That will typically be used to determine your static head. So next up, you need to know how far are you pumping. So typically your horizontal run, how long your pipe is, as well as what diameter and type of pipe is being used. So Schedule 40 pipe versus SDR 21 is going to have different effects on the pressures in your system. You also need to know what fittings and how many do you have in your system. So that's going to be your check valves, gate valves, your 45-degree elbows, 90-degree elbows, things of that nature. And then lastly, you need to know what are you pumping to? So are you pumping to a gravity sewer? Are you pumping to a septic tank? Or are you pumping to some kind of pressurized system? So everything on this slide, other than what your design flow is going to be used to determine the pressure or your total dynamic head that your pump needs to be capable of pumping against. And we're going to go a little bit deeper into that in the next few slides. So first off, though, let's cover pump performance curve. So every pump has a performance curve showing its relationship between flow and total dynamic head. So along the bottom here, you have your flow rate. That's going to be your x-axis. That's typically going to be in gallons per minute or liters per second, like I said before. And then your y-axis is your total dynamic head, which is typically in feet of water. So here's an example of what a pump performance curve looks like. Pretty much every pump performance curve has a downward slope on a graph like this. That's because when the pump is putting out more flow, it's not able to handle nearly as much pressure and vice versa. So first off, you'll notice that the pump curve cuts off not exactly at zero. I would say usually the pumps, especially for Zoller, cuts off at around 5 feet of head. The main reason for that is not because the pump won't continue to operate past that point. It will, but it's going to be drawing more amps than what that motor is rated for. So if you go to the right of the curve, so if you go off of the curve, you're actually reducing the life of that pump. So you always want to operate on that pump curve at all times. So just as an example on how to read these, it's pretty simple. You go from your x-axis from, let's say you need 20 gallons per minute from a pump. So you go up to the pump curve itself, and then you just go over to the y-axis, and that's going to tell you the pressure that that pump can handle at 20 gallons per minute. Just as another quick example, at 30 gallons per minute, this pump can only handle about 15 feet of head. So you see that with the increase in GPM, it decreases in pressure capability. And then lastly, this is what we call the shutoff head of the pump. This is mainly where that pump is not going to be moving any water. It's still going to be operating, but that water is going to be stuck in that pipe. It's not going to really be moving anywhere because that pump can't overcome the pressures in that system. And then there are various types of pump performance curves that you'll see. The purple performance curve on here sort of has a knee. At that knee where that bend happens, that's actually where the maximum amperage point is for that pump. And then you have pumps that have a lot more flow and a lot more pressure capability. And then you also have pumps that have very low flow capability, but very high pressure capability, such as this maroon curve here. And actually, that maroon curve mirrors typically what grinder pump curves look like, at least on the smaller end. So 1 and 2 horsepower grinder pumps typically have curves like this, where it's a very steep drop comparing flow to pressure.
And just a quick question on the curve side. So you mentioned the 30 to 15 design point versus say your 20 to 20 design point that's kind of more in the middle. Is there an effect long term on the pump if you're operating on the curve still, but more towards one edge than the other?
Yes, and I actually do get into this a little bit more later in the slides, but real quick on that, just to answer the question, you want to operate to the center of the curve if possible, because if you're operating too far to the left of the curve, or at least to the left of the curve in general, that pump is doing a whole lot more work, which means that, or it's essentially losing efficiency in that end. Whereas if you're operating to the right of the curve, that pump is drawing more power and is reducing its life. So you kind of want to operate in the center. And I have a little bit of a graphic to show that later in these slides.
Okay, perfect.
All right. So continuing on. So why sizing matters? So it's more than just your rated horsepower. So up here, we have 4 different pump curves, curves for 189, 295, 631, and an 840. You'll see here that the 631 is that very long curve that goes very far to the right that can get very high flow rate. However, you'll notice that its shutoff head is about 35 feet, so it can't handle a whole lot of pressure. However, with the 840, it can go up to about 42 gallons per minute, but it can go to 104, 105 feet of head. The main reason why I'm showing this is because these are all 2 horsepower pumps. You never want to size based on horsepower alone. The main things that affect pump performance are these factors here. So your impeller style and your impeller size. So if you're using a vortex impeller versus a enclosed impeller, that's going to have a major effect on the performance of that pump. The motor speed. So typically, most pumps are going to operate either at 1750 RPM or 3450 RPM. Some pumps operate a little bit less, but for the main thing, you're going to see those 2 speeds. And with that, that's going to affect that pump performance as well, because that faster speed means that you're pumping a whole lot more water. Your pump housing design is also going to affect it, mainly where that water is moving through the housing itself, as well as the solids handling capacity and the discharge size of that pump. All of these things are taken into account when a new pump is being designed and tested. So continuing on why sizing matters. There is a balance when you are sizing a pump. Undersizing a pump can cause a few issues, such as overflow. If your pump cannot keep up with the liquid or the wastewater that is coming into the basin, wherever that pump is located, you're eventually going to have overflow issues with it, and you're going to have to replace the pump with something that can handle those flows that are coming in. Another issue is clogging. So you need at least the minimum velocity of 2 feet per second to keep solids suspended through a pipeline. So this is mainly something you need to worry about when you're working with wastewater applications. And actually here at Zoller, we recommend somewhere between 3 to 5 feet per second being the sweet spot to prevent any kind of clogging issues. The main reason why we recommend that is because products nowadays have gotten to be a lot more water conservative. So specifically toilets, just to keep that in mind, toilets in recent years have dropped in the amount of water that is used when flushing, which means that you have the same amount of solids that are going into your basin, but you have less water going in there as well. So you need to keep the lesser amount of water moving faster to keep those solids moving. So that's why we recommend 3 to 5 feet per second, just to make sure that there's not any kind of clogging issues. This is actually an example of a pipe that has slowly clogged up due to the velocities not being met. And then another example of a pipe that has actually fully clogged, and that pump just cannot overcome the pressure that is being put back on it from this clogged pipe. So no one really wants to go down and dig these pipes up and replace them. It is not a clean job. Oversizing can also be problematic. So one thing is short cycling. So pumps, typically when you're turning them on, they draw a lot more amps at first than when they start to run continuously. So if you're constantly turning that pump on and off, typically we recommend 6 to 10 starts per hour. If you're going above that, it's possible that you can short cycle that pump and burn out that motor prematurely. Another thing is power consumption. So obviously larger pumps are going to draw a whole lot more power. So you don't really want to put a commercial level pump into a residential system. That's going to not only cost more upfront, because the larger pumps are going to cost more, the larger system is going to cost more, but the pump is also going to draw a lot more power from that location. So those are some things to keep in mind. Going back to that 3 to 5 feet per second, typically the 8 feet per second is usually the maximum that we recommend in really any kind of application, mainly because water is naturally erosive. So if you're going above 8 feet per second, you're increasing the possibility of the water eroding your valves and fittings and causing premature failure from that end. So continuing on why sizing matters, the dangers of crossing over from another manufacturer. You got to ask, is the application correct? And was the original pump sized correctly? It's very possible that just because someone else has already done the sizing and everything, and you're just crossing over from their pump, it's very possible that they didn't do the sizing properly. So it's always good to go back and make sure and start with those questions that we've already covered to truly figure out if the pump that you've crossed over to is going to work in their application. You may just be adding fuel to the fire and failure of another pump. So that's the added value of knowing the right questions to ask from this presentation. So going back to pump sizing, 2 things are necessary to size any pump. First off is flow. You need to know what your flow rate is. Typically, it's either going to be in gallons per minute, liters per hour, or cubic feet per second. You also need to know what your total dynamic head is, or your pressure. This is a measure of the back pressure from the system at a given flow. So your total dynamic head is going to change depending on the flow that is going through that run of pipe. So This is typically going to be measured in feet of water. Now, typically when you hear pressure, you think of something like PSI. However, feet of water is just a conversion from PSI over to feet. This is just a measure of the depth of that water. The pressures that you would find at, say, 10 feet of depth. That is what that measure is. And lastly, your total dynamic head is going to equal your static head plus your friction head plus your operating head. And in the next few slides, we're going to break that down a little bit more. Flow and total dynamic head together provide what we call a design point. So this is what you're going to make your pump selection based off of. So first off, your design flow. There are some considerations to be made when it comes to determining what your design flow is. For sewage applications, you're going to be using one of these three methods to figure what your design flow is. You're either going to use the fixture unit method, the existing water usage method, or the population method. The fixture unit method is sort of an older method that I'm not really going to show here, but just to explain a little bit, it's just taking into account the number of fixtures that you're going to have in, say, an apartment, such as a sink, a shower, a toilet fixture, things of that nature, and you're going to use that to determine your flow rate based off of a chart. The existing water usage method is primarily used for replacement pumps. So after, I'd say, about a year, you'd have plenty of data to go off of from an already existing application to determine what the flow rate you actually need. Typically for a lot of applications, when we're using these other two methods, it's really just a assumption or best guess, and typically they can be a little bit more conservative. So if you are replacing a pump, it is possible to use data that you've already gathered to make a better selection for the long run. Then you also have the population method, which is a newer method that just uses the number of people that you're expecting to be in a building. So for example, if you have a restaurant, typically restaurants, you can pull this from charts that you can find online, but typically for restaurants, it's going to be about 10 gallons per day per person. So if you're at 200, that's going to be 2,000 gallons per day, and you can use that value to find the gallons per minute that you need. For effluent applications, this is typically driven by your dispersal methods. So D boxes, pressurized manifolds, low pressure pipe systems, and drip systems are all going to have their own flow rate requirement or maximum flow that they can handle that you can size off of. And then lastly, with groundwater and stormwater, typically with sump systems, you're just going to base it on the square footage of basement and the soil type, whereas with stormwater, it's going to be based on the square footage of the collection area, rain intensity, and runoff coefficient, which is all found in an equation for that. So now moving on to your total dynamic head. There are three parts to total dynamic head. First off, you have your static head. This is your elevation difference between tank water level and where water meets the atmosphere. Then you have your friction head. This is your head loss in the system due to friction between the water and your pipes, your fittings, your valves, etc. And lastly, we have your operating head. This is the required pressure at the end of the system. So if you need to meet a certain distal pressure, that will be calculated in. If you have a certain force main pressure that you need to overcome, such as in a low pressure sewer system, that value is going to be added at the end of your equation. Typically, for most applications, you're not going to see operating head. If you're pumping to something like a gravity sewer system, your operating head is going to be 0. Since there is no pressure that is being put back on your pump from that gravity sewer system. So adding all these three together will be your total dynamic head. So let's break down friction head just a little bit more. So friction head is going to vary with the length and diameter of your pipe and the flow. So we need 4 pieces to determine the friction head at a given flow. First off, you need to know what type of pipe that is being used for the project. You need to know the nominal length of your pipe. That's going to be your length of straight pipe that is being put in place. You need to know the diameter of the pipe. And then lastly, you need to know your equivalent length of fittings. The first three are fairly easy to determine. There's not really any kind of calculations that go into making that determination. But number four, your equivalent length of fittings, you're going to need to use that a calculation or an equation to determine the pressure that those fittings are putting back on your system. So typically you're going to use a chart like the one here below. So a given fitting will have the same friction head as a certain length of straight pipe. So on the left here, you have your types of fittings. So you'll have a 90-degree elbow, 45-degree elbows, your T's, check valves, gate valves. And along the top, you have your nominal pipe size. So this chart goes up from 1/2 inch to 12 inches. These charts can get a lot bigger, but with most pump systems, you're mainly going to be in these size ranges. And this is also going to be based on the type of pipe that is being used as well. So keep that in mind. So a check valve, a 1 1/4 inch check valve, is equivalent to 11.5 feet of straight 1 1/4 inch pipe. So how did we determine that? So all you have to do is go down to this chart, find your 1 1/4 inch pipe, and you find the fitting that you're converting to or converting from, and you'll meet in the middle. And that is going to be your equivalent length of straight pipe. And we're going to use that in determining your total friction head loss. So once you have all these values down for each fitting, you're going to take your total length of pipe and add that value to your equivalent length of fittings to get your total equivalent length, which is going to be used to determine the friction head in your system. So this is the second chart that you're going to use when you're determining your friction head. For this chart, you can see on the left here, you have your gallons per minute. This is going to be based on your design flow rate. And then along the top, you have your pipe size or your pipe diameter. So what we're primarily interested in is this loss column here, which is going to be your sort of conversion factor when you're determining your friction head loss. We also have the velocity here. So these charts are very handy in determining what velocity your water is going to be hitting when it's going through a certain size pipe. One thing that you'll notice here are these gray boxes. So those gray boxes highlight 2 feet per second to 8 feet per second. So typically when you're using this method, as long as you're in that gray box, you're good. You're hitting those scouring velocities, but you're not getting too erosive for your fittings that are in your system.
And just a quick question coming in here from the chat. Are these proprietary Zoller charts or are they readily available anywhere?
Readily available anywhere. You can look them up online. This chart here, like I mentioned before, it depends on your type of pipe that is being used. So a SDR21 pipe is going to look different from this chart because this chart, I believe, is PVC Schedule 40.
Yeah.
But no, you can find these online anywhere. On our website, we actually publish a few of them just for a quick reference for anybody that may be on there. But no, they are not proprietary.
Perfect. It's just industry standard.
Yep.
And then, so one of the other questions that, it hasn't come up here, but it does come up almost, very regularly when engineers are reaching out, maybe early in the design stage, and they don't necessarily have all the friction loss. They don't have necessarily the horizontal run length. They just, it's an elevator pump. It's going to go up approximately 20 feet is what they say.
Mm-hmm.
How important is the accuracy of the length of run versus just an estimate?
I'd say it's going to completely depend on the system because if like you said, it's pumping up 10, 20 feet or something, and it's going to gravity after that or something, that length of pipe is not very long. But if you have a system that may have something like over 1,000 feet in length, I would say, and that's not a hard number, I'm just using that as an example, but I would say it's important to take that into consideration because as I'm going to show you in some of these calculations, the longer that run of pipe, there's a whole lot more friction that is going to be put on that, or a whole lot more pressure that's going to be put on that pump from that additional friction loss.
Yeah, I think
So
we'll see it as we get into the examples. We were talking at the beginning about, we just had the Derby down south in Louisville, but we had done a track up here in Canada. I won't say names, but big racetrack, and they were going all the way across the parking lot with the pump. So all of a sudden that flow rate and that length really does add up. So I
yeah,
think your application dependent answer, as annoying as it often is to hear as the engineer, as the design engineer, it really does come down to the specific application.
I agree. Okay, do we have any more questions before I continue on?
Looking good. Nothing coming in right now.
Fantastic. Okay, so continuing on. So just as a quick example on how to read one of these charts. So let's say your design point is 25 gallons per minute and you're in the 1.25 inch pipe like we've gone over earlier. You just meet in the middle between these two, the row and column, and you'll find that you have a 7.89 friction head loss in feet of water per 100 feet of pipe. So that per 100 feet of pipe actually matters a lot for this type of uh, for any system, mainly because that's a conversion. So if you have 200 feet of pipe, then that value is going to double. If you have 50 feet of pipe, that value is going to be halved. That's why it matters about the length of pipe that you have in your system, because already you can see that these values can get very large. And then you also should check your velocity. We're in that gray box, 5.36 feet per second. So that's pretty close to that 3 to 5 feet per second range that we recommend. So that's good to go. So friction head calculations. This is the equation that I've been referencing. This is mainly why you want to go over those two charts from before. So your friction head is going to equal your friction head factor multiplied by your total length of pipe, your total equivalent length of pipe, divided by 100. So as two quick examples here, you have loss in 50 feet of pipe, or 50 feet being your total equivalent length, which is including your check valves, gate valves, anything in that system. So you take 7.89 times 50 divided by 100 to get 3.95 feet. Whereas your loss in 200 feet of pipe is equal to 7.89 times 200 divided by 100 is 15.78 feet. You can already see that difference of 150 feet has already added on about 11 to 12 feet of friction head loss. So once you have your friction head, you're going to add that to your static head and your operating head if that's something that you need to account for to get your total dynamic head. You will then use these values to plot your design point and pick a pump. So the design point is a combination of flow and total dynamic head. So your flow is equal to 25 gallons per minute for this example. Your static head, we're going to say, is 10 feet, and then your friction head is 8.9 feet. We're just going to say we're going to a gravity sewer. So with that, you can determine that your total dynamic head is going to be about 18.9 feet. You will then plot the flow and total dynamic head on the same chart that we put pump curves on to determine what pump to select. So here you'll find 25 gallons per minute. Here you'll find about 19 feet of head, and you'll meet in the middle for your design point. Once you have that design point, you're going to compare that to some pumps that you may want to select and make your selection. So one thing to note is only pumps which pass over or directly through the design point are sufficient. So with that, we can get rid of this maroon curve there, because that pump cannot handle the flow and pressure. Generally, the pump passing closest to design point is the most appropriate. So for this application, we would recommend choosing the orange pump. However, in some instances, it may be beneficial to instead go with something like the purple pump here, just because if, say, you can get the orange pump in 3 days or in 8 weeks, but you can get the purple pump in 3 days, that may be a consideration to take into account, depending on what are the immediate needs of your project. But for the most part, you're going to be going with the pump that most closely fits the design point. So with that, we have an example to quickly run through. A contractor has asked you to specify a pump for a small commercial building. They have given you the following information. So your design flow is 35 gallons per minute. You have 300 feet of 1.5 inch Schedule 40 pipe. You have one check valve, one gate valve, and 4 90-degree elbows. You have 10 feet of vertical rise, so that's going to be your static head. And then lastly, your voltage in phase is 230 volt one phase. So this is likely going to be a smaller residential type pump or maybe a small commercial system. But I would like to point out that you're never going to get all of this info right off the bat, which is why it is important to have these questions answered or at least know what questions to ask so that you can size these systems properly. So real quick, running through the fittings conversion. So for the 1.5 inch check valve, you're going to go down to this chart below, find the check valve. You will then find your 1.5 inch pipe, and you'll meet in the middle. So you'll see there that yellow highlight is going to be your equivalent length for one 1.5 inch check valve. So you take the total number, your quantity multiplied by your equivalent length. We only have one. So that's going to be 13.4 feet. However, we have 4 90-degree elbows, so we need to take that into consideration. So going down to the chart, you'll see that one 90-degree elbow is equal to 4 feet of straight pipe. So we'll take that quantity and multiply it by that value to get 16 total feet from all your elbows. And then lastly, you have one gate valve. So on the chart, it says 1.1 feet. So 1 times 1.1 is 1.1. You'll add all three of these together to get your total equivalent length in fittings being 30.5 feet. You're going to add that to the horizontal run when you're computing your friction head. Real quick, determining our friction factor for this example. So the pipe material is Schedule 40. So that is, as I've said before, these charts are based on the type of pipe that is being used. So it is important to make sure you're looking at the correct chart. The required flow rate is 35 gallons per minute, and we are using 1.5 inch pipe. So going down that loss column, you'll find that your friction head loss is 6.95 feet of water per 100 feet of pipe. And then your velocity is 5.51 feet per second. We're in that gray box. We're good to go. So calculating your friction head. So your total length, so we have 300 feet of straight pipe, and we calculated that our total equivalent length in fittings is 31. So you're just going to add those two values together to get 331 feet. You then, we've also determined that our pipe has a loss factor of 6.95. So using these two values, we're going to plug it into our friction loss calculation. So our length value is 331. Our loss factor is 6.95. And then that 100 comes from the per 100 feet of pipe on the previous slide. Putting that together, we will find that we have about 23 feet of friction loss in 1.5 inch pipe at 35 gallons per minute. So now once we have that, we can calculate our total dynamic head. So static head plus friction head plus your operating head. So your static head was given to us at 10 feet. That's your vertical rise. Your friction head is 23 feet. And I know we didn't really say anything about it, but we're just pumping to a gravity sewer. So the operating head is going to be 0. So our total dynamic head, adding all three values together, is going to be 33 feet. Now that we have that, we have our design point. So that is 35 gallons per minute at 33 feet of head. So let's select our pump. Up here, we just have pump performance curves for X, Y, and Z. And we're going to plot our design point on here. So with that, our best selection in this case is going to be the Y pump, just because it is the closest to that design point. You're not going to get a whole lot more flow out of it. So you're not going to be, say overloading the system or anything with a lot of additional flow. Do we have any questions before I move on to system head curves?
Yeah, actually. So there's just one of the questions, I guess, circling back to the issues in oversizing. So we're looking at this, the Y is our best option. If you end up selecting the Z or the Z model, depending on where you are, if you select the Z, what are the impacts that that's going to have on the pump, the life expectancy, or the project?
Um, I think the life expectancy for this specific application, you'll notice that you're likely going to be operating far to the right of that pump curve. So the life expectancy is likely not going to really change. Again, you need to be more towards the middle to be the most ideal. But in most cases, if the pump curves are similar, your life expectancy is not going to change. The main thing to worry about is how much flow that larger pump may be putting out. That is where you may want to go back and check the your velocities that are going to be going through your pipe, as well as we're going to see in the system head curve section. But that's how you're going to determine if your pump is going to be able to handle, or if you're going to use it to determine what your flow rate is exactly from certain pump models. So you can kind of compare pump models, compare maybe larger sized ones, and see how much that flow rate actually changes.
Perfect. And then, so yeah, I guess the chance with the super high could lead to some short cycling and affect
Yes.
the
Yeah.
performance. They ask if a VFD is appropriate for these pumps. I don't believe that VFD is available. Variable frequency drive is available in some pumps yet. Correct me if I'm wrong.
In some pumps, yes, we've spec'd out a couple for sump pumps. You mainly want to use VFDs and sump pump applications when you have an area that gets a lot of variable levels of rain. So maybe you want to keep that pit dry consistently. So sometimes it may rain uh, you know uh, a significant less amount than some other time. So you're going to want, you can use a VFD to kind of fluctuate when that happens. But they are available. That is something that we've done before.
Okay. And then a couple of just real quick ones I'll knock off as we go here. So does the static head have anything to do on the pump performance curve? As we just covered, the static head adds to your friction loss head and your operating in order to get that design point. And then more details on the operation head. So operation head would be if the the pressure at your delivery of the water, if you're not going to gravity and you have to overcome an operating pressure, that's when that is included, and that would just be added to your combination there.
Yes.
And then I guess the last thing, is there a sweet spot for the amount of runtime on a pump? Are you looking for 3 minutes, 8 minutes, 10 minutes, an hour? What is the ideal runtime, or just a quick range, similar to how you have that ideal sweet spot for the other your feet per second?
Yeah, so typically for smaller motors like 1 horsepower or lower, a minute runtime is usually the recommended spot. Typically those pumps aren't drawing nearly as much amps as say a larger motor pump, so they're less likely to burn out like that. But as you get to like 3 horsepower to 5 horsepower, or even 7.5 horsepower, 3 minutes runtime, and even getting up to 10 horsepower plus, 5-minute runtime is a good target to hit. But the runtime isn't necessarily what we're worried about. We're more worried about how often that pump is turning on and off per hour. So like I said before, about 6 to 10 starts per hour is a sweet spot for most pumps. Just because as you get up into those higher start times, or the higher number of starts per hour, that's when it can become problematic on that motor starting so much.
And just as I know we're approaching the end of the hour here, I think we're going to run a little bit long, but for anyone that does need to necessarily drop off, and we had a question asking about recording of this presentation. So I'll just pop this in the chat here. You can visit any of this session or any of our previously recorded sessions will all be hosted here, atspec.com/ATS webinars, and they're all available to review at any point in time. So with that, we'll pass it on and we'll just power through.
All right, sounds good. I will try to, this section's a lot shorter than that first section. So what we just went over was the traditional method of sizing. This is what is primarily used to have a quick selection for a pump. We use this to determine a design point. It's derived from charts, and it gives you your flow and total dynamic head. The only problem with this is this does not provide the big picture of pump operation. And that is where system head curves come in place. So, question, you have figured a design point and you've selected a pump. However, the design point isn't on the pump curve. Now what? How do we know what that pump is actually pumping at, right? You're going to use a system head curve to determine exactly where that pump is on that curve, or on the pump performance curve. So the system head curve shows how the pressure changes as flow changes through the system. So here is a singular design point. However, a system head curve is actually based on a multitude of design points, because as I said before, the pressure is going to change with the flow rate through your system. So all you're going to need to do is, I'll go over the equation a little bit later, but you're going to use an equation to determine various pressures at various flow rates. And once you start to map that out, you start to get something that looks like a curve. And doing a line of best fit will give you that system head curve. A system head curve, as you can see here, is the opposite of a pump performance curve. It has an upward slope rather than a downward slope. That's because with systems, the more flow that you're putting through it, the more pressure that system is experiencing and putting back on that pump. So now let's compare your system and pump curves. So we have our design point here, and we have our pump performance curve. So if you map out that system head curve, you're going to get something that we call the operating point. That is the intersection of these two curves. So that operating point is going to be the actual flow and pressure of that pump. So your system head curve is affected by the same things that affect your total dynamic head. So your static head, your operating head, the flow rate through your system, the diameter of your pipe, as well as your length of pipe, or your total equivalent length of pipe, and then a C value. The C value is it's a friction factor for whatever pipe you're using. Typically for new pipe, you're going to be at about 140 to 150 for that C value, whereas for older pipe, you're going to be around 110. And those are typical values that you'll see. So the system head curve is derived from this equation here, which is called the Hazen-Williams equation. So your total dynamic head is equal to 10.44 times L times, L is your total equivalent length, and that 10.44 is your, it's a conversion factor, because these values aren't all in the same units. So your length is going to be in feet. Then you have your flow rate, which is to the 1.85 power. That's your Q value, which is going to be gallons per minute. And then you divide by the C value to the 1.85. Your C value is just it's just a coefficient. You're not, there's no units tied to it. And then lastly, you're also dividing by the diameter of your pipe to the 4.87, being it's not going to be the nominal diameter, it's going to be your inside diameter. So say for a 2-inch schedule 40, you're not going to plug in 2 inches to this equation. You're going to plug in 2.067, which I believe is the inside diameter for that type of pipe. So that's going to give you a more accurate value. And then you're going to add your static head and your operating head at the end of the equation. So plotting a system head curve, you're first going to start with your static head, because if you notice with this equation, that static head and your operating head as well is your y-intercept. When everything else is 0, that static head is still going to be a factor in your system. The height in which you're pumping up is not going to change. So first you plot your static head. Then once you have that, you're going to plug everything else into that equation to plot out your system head curve. Now, the great thing about having this data in front of you is you can manipulate it to better fit the pump that you're selecting or the system itself, or the system design, to better optimize it, make it more efficient. One way that you can do that is by actually increasing the friction in your system. Mainly, you're going to do that by either decreasing the size of your pipe, because you'll notice with that previous equation, when you decrease the size of the pipe, your total dynamic head is going to increase. Whereas if you increase the total equivalent length of your pipe, that is actually going to also increase your total dynamic head, so your final values. So that is one thing that you can do. If you want to have less friction in your network and in your pipe system, you're going to instead reduce the amount of friction for that system. So you typically either increase the size of your diameter or decrease the length of pipe that you're using. For the most part, you're really just going to be changing the diameter and type of pipe that you're using. That will have the largest effect on your system. Again, like I said before, if you do have operating head, that's also going to be a part of your y-intercept, which is simply going to move your system head curve upward. So keeping it to the center. I know we've already covered this, so I'll go through this a little bit quickly, but if you're operating to the left of your pump curve, that's going to be your least efficient operation, which will lead to wasted energy. I like to equate this to hiking up a mountain with a backpack on your back. You're not making a whole lot of progress and you're losing a whole lot of energy. So you're going to get tired a lot faster. That is the same thing for a pump. Whereas if you're operating to the far right of that pump curve, that pump is going to draw higher amps, it's going to run hotter, and it's going to shorten its life. I like to equate that to running at a dead sprint. You're making a whole lot of progress, but it's not something that you can really sustain. Whereas right here in the center is going to be your best efficiency range. That's similar to going for a jog. It's something that you can maintain for a while. You're not wasting a whole lot of energy, and you're making quite a bit of progress as well. So that is why you want to stay close to the center of that pump curve. And that's sort of where system head curves come into place. Being able to map that out and see where exactly you're operating will give you that chance to change your system and increase the life of that pump before that pump is put in place. So with that, system head curves give us data to make the best selection. So as an example here, here's our design point. We have 3 different pump curves. As we've already gone over, we already know that the curve to the left of the design point is not going to work for this system. So we can quickly eliminate that. But now we have to select between 2 different pumps. And the best way to do that is by mapping out your system head curve. Now you can see here the 2 different operating points for these pumps. With the original traditional method of sizing, you may have thought that that curve that is closer to that design point was going to be a better pump for the application. However, by using the system head curve, we can see that you're operating far to the right on that pump curve. Whereas for that longer curve here, you're actually dead in the middle. So you don't have to change anything about your system, and you're operating at the best possible efficiency for that pump. So for this application, we would select that longer pump curve. So by using our system head curve, we actually increase the life of the pump in the system and decreased something like downtimes, or we've just made it a lot more efficient. So now getting on to correcting a low head situation. So I know I've talked about static head just being from your minimum liquid level in your basin or from your pump to the outfall of your system. What if you have something like a system with a high point and then your outfall being below that pump? How is that going to affect our pump selection in our system head curve? Well, let me show you. With that static head being factored into this, you'll notice that the design point is at a negative point for the system. So you just think, oh, any pump is going to be able to handle the pressures in the system. But that's simply not true. By using the system head curve, you can clearly see that we're actually operating to the far right of that pump curve. You're operating off of that pump. So that means that you're going to quickly burn out that pump. It's not going to be able to handle it. So how do we fix that? We fix that by introducing friction into our system. So the main way that you can do that is increase the length of pipe, or which is the typical thing that we look at, is changing that pipe out for either a different type of pipe or a smaller pipe diameter, which will increase the friction in your system and will actually get that system head curve crossing that pump curve. So that is something to take into consideration. Another thing to take into consideration for a system like this is all the critical locations. A critical location being the outfall and that system high point where that water is going to bleed off from. So for this specific system, we have point A and point B. So what we're actually going to do is we're going to do a system head curve for each location. The main reason why you want to do that is when that pump turns off, all of that water is going to bleed off between A and B, and you're left with the water in that pipe from that pump to point A. The reason why it doesn't bleed back into your pump station is because you always want to make sure that you have a check valve in that pump station to protect it and to prevent any kind of backflow from your system. So by mapping out your system head curve at point A, by just taking into account that static head when that pump first turns on, because it has to overcome that pressure, you'll see that that system head curve is like this. But you also have to take into account that low point B and map out that system head curve as well when your static head is negative. So for this system here, you can clearly see that this pump is going to work for both critical locations. But if you had only mapped out for the previous one, the original system, or the high point with this original system head curve, yeah, that pump would operate at the beginning from that high point and not overheat. But once it drops down for this system head curve specifically, it will overheat. So it's important to take into consideration all of the critical locations. And you can also have instances as well where your static head at the high point is actually above the shutoff head of that pump, but you'd only be considering that low point in the system where you'd be like, yeah, any pump is going to work here, but that pump wouldn't be able to overcome the initial pressures of that system after the first time it is run. So another thing, using system head curves and VFDs. So you always want to map out a system head curve when you are using a VFD for a system, mainly if you're using a VFD on sewage applications. So the main reason for that is when you're using a VFD, it's going to affect your system head, or it's going to affect your pump curve. When that pump is operating at a slower rotational speed, it's going to decrease the flow that that pump is putting out, right? That's the whole point of using a VFD. But with a VFD, you also run into issues where you're dropping that velocity through that pipe network as well. So for this specific one, if you hadn't mapped out that system head curve and you wanted to operate at 30 hertz as well as 60 hertz, you'll notice that you're not hitting that 2 feet per second scouring velocity for that network, which will mean that you're going to run into clogging issues for that system. So that's why you always want to take into account your system head curve, so you can determine all of your flow rates at the various frequencies or various rotational speeds for that pump at whatever speeds you want to operate at. So what if you have a pump curve that has a whole lot of static head but not a lot of friction head? So let's map out that system head curve in VFD with it. You'll notice here that your operating head or your operating point for 30 hertz drops below the static head of that system. When that happens, if you're operating at 30 hertz, you're not moving any water at all. That pump's going to be operating, but no water is going to be reaching its destination. So with that, it's always a good rule of thumb to consider. VFDs are a lot less viable when your static head is more than or equal to 50% of your total dynamic head, or if you have flat system curves like this one here. When you have a flat system curve, your flow rate is dropping significantly with every single speed change. So real quick, just going through these are the last couple slides for this presentation. Just going through this, you'll notice here that when you change that pipe diameter between 4-inch system head curves and 8-inch system head curves, you'll notice that there is a major pressure difference. This is where you can either get your flat system head curve, or you can start to get a lot more of a sloped system head curve. This is also comparing between one pump and two pumps. You may have systems where you want to make sure that you can actually turn on your second pump and get double your flow rate. If you want double your flow rate, you're going to typically want a system head curve like that flat curve there, because you will actually be getting close to the flow rate that you want. The C value is just an example showing that that C value really doesn't change the pressures in your system all that much. So it's not really something to consider. And you can only really consider that between something like ductile iron pipe and plastic pipe. And then lastly, this is just another curve showing the difference between when you consider your static head and your operating head, and where exactly you'd be operating on your pump curve when all of these things are taken into account. So with that, that is the end of this presentation. Do we have any questions that I need to address?
No, I think nailed it there at the end. That was I know that's a lot of detail to cover, and frankly, there probably are additional questions. What I would say is feel free to reach out to me, Zach at atspec.com. I'll be happy to circle in. We can bring Zoller and all the other application engineers into the conversation. We can get that conversation going with everyone. If you have maybe more detail that you want to understand, if you want a similar presentation set up for your specific firm, we can get that organized as well. We certainly find a lot of people that attend our ATS universities, they end up having a second presentation that they want set up specific for their firm. So we can get Chase or any of the other application engineers to join us in that conversation. One thing I did want to show, just I'll take over screen sharing here just for a real quick second. Not going to jump in and do a full demo, but did want to show, for those of you that, again, may or may not be familiar with ATS, this is the service that Zoller partners and sponsors on our system. So it's important to know, you go to atspec.com, you can sign up for free. Everything's paid for by the manufacturers in a sense. It's free for architects, engineers, design, build contractors to create an account and log in. Before you even log in, though, you can go to these Architects and Engineers tab, go down the Learning Hub, and find the webinar recordings for the previously recorded sessions that we've had. like I mentioned at the outset, we do a wide variety of either deep dives into a product like we just did today, application overviews like we just recently did for educational sphere, the hospitality sphere, we've done healthcare, or maybe specific product groups like we talked about previously. Some that are more code based, some that are more product based. And then once you're done and you've logged into your account, you can then start adding those into your various folders on ATS. The idea is that you have either the open catalog here, you can create a project and start, essentially drag dropping into your project folder, or if you've got a master setup, that's what my team is here to do. So if you are doing repeat work on either an application type or repeat work on a owner group, let's say Tim Hortons or Starbucks, everyone knows Starbucks. If you got the Starbucks account and you're doing a number of them this year, reach out to me and my team. We can help you get a master set up. And then when you're in a project, all you need to do is drag and drop, then configure or size the specific product. So you can see we've got a little plus button here. From here, you could create drawing or use your masters to add to this project file. So if you have your branded hotel here, or you go into an ATS template, which is basically an ATS version of a master, we could go and drag and drop our fixtures over, or sinks, or go into our mechanical equipment and drainage area. And you can start with an unsized pump here, and then use the system or the application engineers at Zoller to make it a more accurately sized product. So we can, of course, edit this and then jump into our pump sizing option here and select the pump that we need. You can also go and do it the old-fashioned way, take a little extra steps. You can go to create new drawing. You can see we've got our favorite categories here, all the various pumps and pump accessories. We can go into our pump category, use the pump sizing tools from Zoller that are integrated into the SpecTool here. So use the link, it'll pop open the Zoller pump sizing tool. Once you have an account, you can enter all the details that we talked about today into your static head, get to your total dynamic head with your friction losses, enter your voltage and all the various flow design points to help you. It'll tell you what the appropriate pump is, and then you can find that pump here. So if it spits out, hey, you need a 293, you could then search for the 293. You could filter down here and say, well, I know I need a 293, but I want the 203 phase, and then find your J293, configure it. Are you doing a duplex application or a simplex? We'll walk through, just make a couple of quick selections here. Cord length, as Chase mentioned, very important to make sure you get the right one. Select our basic impellers. We could go with the double seal here or the single seal. That's going to change you from a 293 to a 4293. We'll just go with basic single seal. Now, of course, one other thing, if you want to see those curves, we do have all those curves loaded into the pump spec sheet here. So you can see, you've got the pump's performance curve that Zoller has on the spec sheet. You've got also a nice handy dandy little chart here. So if you're looking at, say, 20 feet total dynamic head, 70 GPM, 100 GPM, whatever it is you have. So once you've configured it, you make it into your selection. It'll recommend, a control panel here next, any of the additional elements of the fixture chain that are required. So this is going to take a look at the amperage, make sure that we select and the correct, it's going to be the Pivot Pro series for this one because we went duplex. I can include an alarm if I want it or not, but this is going to be appropriately, our rules-based system, make sure that you get in the right control panel with that pump. We're going to match the amperage, match the voltage, match the phase, and recommend the right control panel there. Now that you've actually configured your pump, you can then go and download. You can see I've got my pump 1, my unsized pump here. If I want to change this one to SP1, simple and easy to change that. We don't need this one anymore, so we'll delete this. And then we can go up to our download button and download it in a submittal or a schedule in Excel. We've got multiple different written specs in Word. You can get the Revit files, you can get the manufacturer spec sheets, all sorts of different variations of taking the data from this pump and providing it in a format that fits your workflow. Some firms prefer to use a fixture schedule on their drawings or a pump schedule on their drawings. Other firms may have a full 3-part spec for each product category. Other firms, I've seen firms that are just taking manufacturer's cut sheet, putting that on the drawings and having a generic open output spec. You can see how quickly it downloads here before I even explain all the different options it's available. So I can then go into my pump sizing webinar here, and we've got all these different formats that are now available here. I'll pop open, let's pop open a submittal real quick. And then you would just take this information, copy and paste it, either onto your drawings, or if you want the written spec, we'll go with the long spec format here. This is like ATS's version. We do have a master spec equivalent version as well. That's the CSI 3-part spec that follows the industry standard 3-part spec. But again, everything's open and editable. We can then copy and paste and put this into your own written documentation or into your own schedule, which again, we do have that schedule format here as well, where it's going to have all the appropriate headers for the pump category, include all the notes and comments that you make along the way. So yeah, that's the very quick, short version. I appreciate everyone giving us extra time today. I recognize we ran over. We'll change it from a CPD hour to a CPD hour and a half when we send out those certificates of attendance. Thank you, Chase. That was great information. I really appreciate your time today. I learned a couple of things along the way, and I've been doing these presentations with, Zoller for, a decade now that they've been partners with ATS. So, there's always something new to learn when it comes to pump sizing. There's always something new to learn when it comes to all our various plumbing products. So thank you. You did a great job. Hopefully everyone that was on the call took something away as well. If you do have any questions on either, follow-up questions on the product we just discussed today, send it to me at zach@atspec.com. If you would like to set up a more detailed conversation specific for your firm, you can reach out to me as well. And if you need help getting your masters, or you want a quick demo again on the SpecTool, all of our market development team is happy to help you out there. So whether it's Mo, Mel, myself, Phil, Natalia, any of our, AK or Kevin or Armand on the spec team, they're all happy to do these demos as well, and we will send those along. I saw a question come in at the end on our CEU certificates. Chase, correct me if I'm wrong. I don't believe this is an accredited, like AIA or ASPE accredited CEU, but it is. We do send out a certificate of attendance that you can use if you are self-reporting your continuing professional development hours. You can use the COA that we'll send out for that. But Chase, do you know, was this an accredited, like ASPE accredited presentation today?
Not that I know of.
Yeah, I didn't think so. We do some of those, full accredited versions. We do always make sure that that note is included in the agenda when you're signing up. So it should tell you whether or not it is or not. I didn't think today was, but it was a very generic one, so it could have been. It wasn't really a branded version, I would say. But yeah, so thank you all again. Have a great rest of the day, and we'll see you next week if you choose to join us again. Bye for now.
Thanks, everyone.